Lesson 28, Fractional Parts of Numbers and Functional Notation. First, I want to review a few problems from the last couple of homeworks that I saw a number of guys had issues with. From problem set 25, first number 23, we had to find the value of a times a cubed minus b if a equals negative 2 and b equals 3. You have to be careful with your parentheses here because a equals negative 2, a has a negative value. So when we plug in the values for these variables, notice I've colored them here for you, this negative 2 for a, we'll put parentheses around it. So negative 2 out here in parentheses, negative 2 in here inside parentheses. Change these to brackets. The first thing we have to do is inside the parentheses, use our order of operations, and the exponent will come first. Notice we have to put the parentheses around the negative 2, or we might do this wrong. Negative 2 cubed is negative 2 times negative 2 times negative 2 is negative 8. Then inside the parentheses we subtract, get negative 11. Negative 2 times negative 11 will give us 22. The next one is 24, where you had this trapezoid that you were supposed to find the area of. The first way, and this is the way I recommend you do it, is by using the formula for the area of a trapezoid. Base 1 plus base 2 times height, all divided by 2. So here the two bases are 14 and 30. Add those together, multiply by the height, which is 12, and divide by 2. So we get 44 times 12 divided by 2. Remember, dividing by 2 is the same as multiplying by 1/2. So we can do those in any order. So we'll divide the 44 by 2 because it's large and annoying. And we get 22 times 12, which gives us 264 square kilometers. The other way you could have done it, if you didn't remember this formula, but you should learn it if you don't know it yet, is you could have broken it up into a rectangle and a triangle, and then figured out the area of each of those and added them. So in that case, we've got two areas to add together. The first one is a rectangle, length times width. 12 by 14, this area here, 12 by 14 kilometers, or 168 square kilometers. For the second one, this triangle, base times height divided by 2 is our formula. The base of it is 16. Notice this longer base here, the total of it is 30. This one's only 14, so the remainder is 16. And then the height is still 12. Divide that by 2, we'll get 8 times 12, or 96. Add those together, you'll get the same answer, 264 square kilometers. From 26, a couple to go over. First off, number 9, 2.5x equals 3/7. To get x by itself here, we use our multiplicative equality property. We divide each side by 2.5. Or you could think of it as using the reciprocal. So 2.5, it'll be a little bit easier if we convert it to an improper fraction first. 5 over 2x. Remember that we could either think of what we're going to do here as dividing by 5 over 2, or we can always multiply by the reciprocal of something to get rid of it. The reciprocal of 5 over 2 is 2 over 5. So we'll multiply each side by 2 over 5. That'll cancel out the 5 over 2 here. And over here, 3/7 times 2/5 will give us 6 over 35. When you have this sort of problem, it's very easy to check it, and you should do so when you have the time and ability to. All that you have to do is just plug in that value that you got for your variable and make sure that you actually get something that works. So let's try plugging it in. So if we said that x is 6 over 35, we'll rewrite our equation, 2.5x equals 3/7. Plug in with 6 over 35. Again, rewrite 2.5 as 5 over 2 times 6 over 35. Multiply, we get 30 over 70, which is clearly equal to 3/7. If you get to this point and these two numbers are not equal, you've done something wrong and you need to fix your work. Next one to go over, similar, negative 3y plus 1/2 equals 5/7. First thing we have to do is we'll do our order of operations backwards. So first we subtract 1/2 from each side. So 5/7 minus 1/2 over here. Convert them so they have the same denominator, 10 over 14 minus 7 over 14. We'll end up with negative 3y equals 3 over 14. We're not done at this point because the variable y is not by itself. We have to either divide by negative 3 or multiply by its reciprocal. And the reciprocal of negative 3, remember we can think of it as negative 3 over 1. The reciprocal is negative 1 over 3. So we multiply by that over here. That'll cancel that out. Multiply by the same thing here. So y is 3/14 times negative 1/3. We get these 3's cancel out. We end up with 1/14, and because we had a positive and a negative, the whole thing is negative, negative 1/14. Last one to go over, another plugging in the values for your variables. Again, notice that one of these variables has a negative value. Please be very careful. When I plug in the values, notice I'm always putting that -2 in parentheses. I just rewrote the equation here, the only difference being that I used square brackets to keep them straight, and I put parentheses around these here. The first thing we do before we do anything else is not cancel out these negatives. Inside the brackets here, we need to use our order of operations. The first thing that happens is our exponents. So -2 gets squared. It becomes 4. -2 times -2 is 4. Then the negative sign applies for multiplication. So we end up with -4 plus 4 inside these brackets. Over here, we have minus -2. We can think of that as plus 2. Now inside of parentheses, we'll add. -4 plus 4 gives us 0. 4 plus 2 gives us 6. -2 times 0 is still 0. Now don't be fooled by the fact that there's this minus here and then the absolute value pipes. The absolute value pipes only tell us to take the absolute value of what's inside them, which is still 6. So we're still subtracting 6 and we end up with -6. Alright, on to lesson 28, fractional parts of numbers. We can use fractions to talk about parts of numbers. We do this all the time. We say things like half of 34, 3/4 of 60, 2/3 of whatever. The things to remember here are what these English words mean in terms of mathematical operations. When we say of, we mean multiply. A lot of guys think it means divide. It doesn't. Please don't make that mistake. Of means multiply. Half of 34 means 1/2 times 34, which will give you 17, which is half of 34. When we say is, that means equals. That one's I think is pretty easy. And when we talk about what number or what fraction, this is a mystery number, a variable. So with this problem here, if the problem they give you is 3/4 of what number is 69, first thing we have to do is convert that into mathematical symbols so we know what we're doing here. 3/4, all right, that stays like that. Of, remember, is multiplication. What number, x, our variable, is equals 69. This is the same problem here, just written using mathematical symbols instead of words. Once we get to this point, okay, we know we just need to divide both sides by 3/4. X is 69 divided by 3/4, or remember, we could multiply by the reciprocal. 69 over 1 times 4 over 3. The 3 and the 69 cancel out to give us 23 times 4, or 92. Slightly different one. What fraction of 40 is 24? Don't be confused by the fact that it says what fraction here. That's still a mystery number. Remember, our variables can represent fractions or decimals or just about anything. So what fraction, x, our variable, of multiplication 40 is equals 24. We just divide both sides by 40. X equals 24 over 40, or simplified to 3 over 8. Functional notation. This can be a little bit confusing. It takes a bit of practice to get used to it. Please don't get too confused with this. Functional notation is just a shorthand for something that we're going to do to a number. And so for example here, say we have x plus 7. We could think of this in a couple different ways. We could say y equals x plus 7. That's what that means is we take some number x, we add 7 to it, and we'll get some other number y. Another way of writing this is instead of writing y, we write f of x, and that's how you read it, f of x. And the of here doesn't mean multiply, that's just how we say it, f of x, f standing for function. The function that we're doing to x in this particular problem means to take x and add 7 to it. Once we have functional notation like this, we can then put in any value for our variable and see what it'll get. So if we say that f of x is x plus 7, then f of 3, we just replace x with 3. 3 plus 7 is 10. We can do the same thing with -2. f of -2 is, instead of x plus 7, -2 plus 7, or 5. This will be particularly handy when we're dealing with some sort of complicated situation where we have multiple different things that we could do to a variable. In that case, we'll actually not only use f, we can use other letters also. So say that we're dealing with some complicated situation where there are 3 different things we can do to x. One thing is we could take x and add 7 to it. Another thing we could do is we could take x and square it and then subtract 2. Another thing we could do is cube x, multiply it by 2, and then subtract 3. We can name each of these in different ways. We can say f of x means to do x plus 7. G of x means x squared minus 2. And h of x is 2x minus 3. We can do this the same way with substituting in a variable for, a value for a variable. So f of 3 means it will plug in 3 instead of x. Instead of x plus 7, 3 plus 7, or 10. G of 3 means we take 3 and we plug it into this function, g of x squared minus 2. So here, 3 squared minus 2, or 9 minus 2, or 7. H of 3 means to take this function, h of x, and apply it. 2 times 3 cubed minus 3. So first we cube the 3 and get 27. Then we multiply by 2, get 54. Subtract 3, we end up with 51. Quick review of the lessons 21 through 24 in preparation for your test. Lesson 21, we had the product rule for exponents. When we're multiplying two things together, if they have the same base, then we can just add the exponents together. So for example, x to the 5th times x to the 7th equals x to the 12th. Even though this is multiplication here, what we do to the exponents is we add them. Because remember, exponents mean how many copies of this are we multiplying together. So we're multiplying 5 copies of it together, then we're multiplying another 7 copies of it together. So in total we have 12 copies of x to the 12th, that are being multiplied together. We can use this to simplify longer expressions, something like this, m cubed p m x m squared x cubed p to the 5th. We've got m cubed times m will give us m to the 4th, times m squared gives us m to the 6th. X times x cubed gives us x to the 4th, and p times p to the 5th gives us p to the 6th. When we have like terms, remember that in addition to having the same variables, like terms have to have the same exponents on the variables. So when simplifying this expression, 2x squared y cubed plus xy minus 8y cubed x squared minus 5yx, I always think it's helpful to rewrite these with the variables in the same order. And I like to use alphabetical order because it's easy to be consistent that way. So the first one can stay the same. The next one, xy, remember that means 1xy. Minus 8x squared y cubed, just flip the order around there, which I can do because this means multiplied together. And then instead of negative 5yx, I'll write negative 5xy. Now I see that even though all of these terms have x and y in them, the first and the third one have the same powers on x and y, and the second and the fourth one also have the same powers on x and y. So we're only going to combine the ones that are alike. So we've got 2x squared y cubed minus 8x squared y cubed. 2 minus 8 gives us negative 6, so we have negative 6x squared y cubed. Then 1xy minus 5xy, 1 minus 5, gives me negative 4xy. And this is why it's helpful to think of xy as 1xy, so we remember what we're doing here is 1 minus 5. In lesson 22, we talked about the term equation, where we have two algebraic expressions connected by an equal sign. Conditional equations are equations that are not always true. They can be either true or false, and it'll depend on the values of the variables. When we have a conditional equation, it will usually have at least one solution or root, and those are the values of the variables that will make it true, or that will satisfy it. In lesson 23, we introduced the term equivalent equations, which are equations that have all the same solutions as each other. The additive property of equality states that we can produce an equivalent equation by adding the same thing to both sides of the equation. In algebra, we're always trying to make our equations as simple as possible without changing the value of anything in there, while still keeping them equivalent. So if we have k plus 2 1/3 equals 2/9, we can produce an equivalent equation to this by adding the same thing to both sides, in this case adding negative 2 1/3. Once we do that, plus 2 1/3 minus 2 1/3 cancel out. We're left with just k over here. And then we have 2/9 minus 21 over 9, or negative 19 over 9. So we end up with an equivalent equation of k equals negative 19 over 9, which very explicitly tells us what the solution of this equation is. In lesson 24, we talked about the multiplicative property of equality, similar to the additive property of equality, except here with multiplication. Now we have to be careful with this one because we have to multiply every term on each side of the equation by the same thing. If we have 4x equals 12, we divide 4x by 4. We can think of division as multiplying by the reciprocal. You can think of it as multiplying by 1/4. Do the same thing over here. We get x is equal to 3. 2/5, x equals 7. Again, we can undo multiplying by 2/5 by multiplying by the reciprocal, 5/2. So that'll cancel out, leave us with just x on the left. 7/1 times 5/2 on the right gives us 35/2.